Have you ever wondered, what if your life wasn't the only version of reality? What if somewhere out there there's another you living a completely different life, making different choices, following different dreams? Is this just a thought experiment, or could it be real? And if it is, how does that change everything we know about existence? In this journey, we'll dive into the science and philosophy of parallel universes, a concept so vast and mysterious that it might just redefine what we think reality is. Imagine this: somewhere far beyond the limits of our perception, there exists another version of you. Not just one, but countless versions. Perhaps in one reality, you're an artist creating breathtaking masterpieces, and in another, you're an explorer charting the unknown. It sounds like the stuff of science fiction, doesn't it? But what if it's more than just a story? What if the idea of parallel universes isn't fantasy, but a possibility rooted in the very fabric of our universe? For centuries, we've believed that reality is singular, one timeline, one set of events, one you. But the concept of parallel universes challenges that belief entirely. It suggests that reality isn't a single thread, but an endless web with infinite possibilities unfolding simultaneously. Think of flipping a coin heads or tails. Now imagine a world where both outcomes happen, each in its own universe. It's hard to wrap our minds around, isn't it? But here's the real question. If these universes exist, where are they? Why can't we see them, touch them, or prove they're real? And if they are real, what does that mean for us, for our understanding of existence itself? It's a mind-bending idea, one that forces us to rethink everything we thought we knew about reality. And to truly explore its depth, we must turn to the science, where some of the most extraordinary theories suggest that parallel universes might be more than just a thought experiment. Parallel universes. What do we actually mean by that? Is it one big cosmic duplicate of our world, or something even stranger? The truth is, there's no single answer. Scientists and philosophers alike have explored multiple interpretations of what parallel universes might be, each more fascinating than the last. Let's start with one idea: infinite possibilities. Imagine every choice you've ever made, the roads you've taken, the words you've spoken. Now imagine every choice you didn't make, creating a new universe, a new reality, where things turned out differently. Perhaps in one universe you decided to pursue your childhood dream, and in another, you took a completely unexpected path. It's like a cosmic version of the choose-your-own-adventure story, where every option leads to a new chapter in an infinite book. Then there's the idea of alternate timelines. Think of history as a single thread running through time. Now imagine that at key moments, pivotal events in history, that thread branches out. What if, in another universe, dinosaurs never went extinct? Or if humanity never discovered fire? Entirely different timelines with outcomes we can't even begin to imagine might be unfolding alongside our own. But here's the twist. These interpretations aren't just philosophical musings. They arise from some of the most intriguing scientific theories. For example, quantum mechanics suggests that every quantum event could split reality into multiple outcomes. In one universe, a particle moves left. In another, it moves right. If you follow that idea to its logical conclusion, you end up with a vast, perhaps infinite multiverse, all springing from the fundamental unpredictability of the quantum world. And what about the cosmic scale? Some scientists propose that our universe is just one bubble in a vast cosmic foam, countless universes existing independently, each with its own set of physical laws. Imagine floating in an ocean where every bubble holds a completely different world. So whether it's infinite possibilities alternate timelines, or entirely separate universes, the interpretations of parallel universes are as diverse as they are mind-bending. But one question remains: if these universes exist, is there any way we can connect with them, or even prove they're real? So if parallel universes exist, what does that mean for us? It's not just a scientific puzzle. It's a question that shakes the very foundation of how we see ourselves and our place in the cosmos. Let's start with the philosophical implications. If there are infinite versions of reality, then who are you really? Are you just one version of an infinite set of possibilities? It's a deeply unsettling idea. For centuries, philosophers have grappled with questions about identity, free will, and purpose. But the notion of parallel universes takes those questions to a whole new level. Think about it. In one universe, you might make a decision that leads to incredible success. In another, you might fail spectacularly. Does that mean your choices don't matter? Or does it mean every choice matters because each one creates a new reality? And then there's the question of fate and free will. If parallel universes exist, does that mean every possible version of your life is already out there, predetermined? Or are you still in control of your destiny, shaping one path while others unfold elsewhere? It's a paradox that challenges everything we think we know about how the universe works and how we work within it. Now let's shift gears to the scientific implications. The idea of parallel universes isn't just philosophical speculation. It emerges from some of the most cutting-edge theories in physics. For example, the many worlds interpretation of quantum mechanics suggests that every time a quantum event occurs, the universe splits into multiple versions. In one version, the particle moves left. In another, it moves right. This isn't just a thought experiment. It's a direct consequence of how quantum systems behave. And on a larger scale, there's the theory of cosmic inflation. According to this idea, our universe may be just one of countless others created during the rapid expansion of space after the Big Bang. Each universe could have its own unique physical laws, making our universe just a tiny speck in an unfathomably vast multiverse. But here's the kicker. If these parallel universes exist, how do we prove it? After all, they lie beyond the reach of our current technology and understanding. Yet scientists continue to search for clues, subtle hints in the cosmic microwave background patterns in the distribution of galaxies, or even phenomena we haven't yet discovered. So what does it mean to live in a universe where infinite possibilities exist, but we may never fully grasp them? Are we explorers of a vast unknown, or merely observers of a single narrow thread? The implications are as profound as they are mysterious, forcing us to rethink not just what we know, but how we know it. Now let's dig into the science, the hard evidence, and the theories that bring the idea of parallel universes out of the realm of imagination and into the world of physics. One of the most fascinating scientific ideas tied to parallel universes comes from quantum mechanics, the branch of physics that deals with the tiniest building blocks of reality, particles like electrons and photons. At this microscopic scale, the universe doesn't behave in ways we're used to. Instead of being predictable, particles exist in a strange state of uncertainty. Here's where it gets really interesting. In 1957, physicist Hugh Everett proposed a radical idea known as the many worlds interpretation. He suggested that whenever a quantum event occurs, whenever a particle has to choose between different states, the universe splits. Each possible outcome happens, but in a different branch of reality. Think of it like this. You're standing at a crossroads deciding whether to turn left or right. According to the many worlds interpretation, you turn left in one universe, and in another, you turn right. Both decisions are real, they just happen in separate realities. This theory isn't just about choices. It's about everything. Every quantum decision creates a branching network of parallel universes, each one following a different path. It's like an endlessly expanding tree, where every split creates new realities. But here's the catch. If these universes exist, we can't interact with them. They're separate like pages in a book that never overlap. This makes the many worlds interpretation both thrilling and frustrating. It offers a stunning explanation for quantum behavior, but leaves us questioning whether we'll ever know if these other worlds truly exist. Still, the theory has its supporters. Many physicists believe it solves some of the deepest mysteries of quantum mechanics. But it also raises profound questions about reality. If the universe is constantly splitting, then how do we define what's real? And if every possibility exists somewhere, does that mean nothing is truly unique, including you? The many worlds interpretation is just the beginning. To uncover even more about the science of parallel universes, we'll need to go beyond the quantum scale and into the vastness of the cosmos itself. If the many worlds interpretation explores the smallest scales of reality, cosmic inflation takes us to the largest, the very origins of the universe itself. This theory not only explains how our universe came to be, but it might also suggest the existence of countless others. So what is cosmic inflation? Imagine the universe as we know it, a vast expanse filled with galaxies, stars, and planets. Now rewind time. About 13.8 billion years ago, everything we see today was packed into an unimaginably small, hot, and dense point. Then in a fraction of a second, something extraordinary happened. The universe underwent a rapid, almost explosive expansion. This is what scientists call inflation. But here's where it gets fascinating. Many physicists believe that this process didn't just create our universe. Instead, inflation might have been happening everywhere, creating countless bubble-like universes, each expanding and evolving independently. Picture a pot of boiling water with bubbles forming, growing, and floating away. Each bubble is its own universe with its own unique physical properties and laws of nature. This means that our universe might be just one bubble in an endless multiverse, a vast cosmic foam where universes are born and die. And here's the truly mind-bending part. In some of these universes, the laws of physics could be completely different. Perhaps gravity is stronger. Maybe stars never form. Or maybe life evolves in ways we can't even imagine. The idea of a multiverse emerging from cosmic inflation isn't just theoretical. Some scientists are actively searching for evidence. For instance, if our universe ever collided with another bubble universe in the distant past, it could leave subtle imprints in the cosmic microwave background, the faint glow of radiation left over from the Big Bang. But even without direct proof, cosmic inflation offers an elegant explanation for why our universe looks the way it does. Instead, we could be one of countless universes, each with its own story, its own reality. So what does this mean for us? If the multiverse exists, then everything we know, our galaxy, our planet, even ourselves, might be just one tiny piece of an incomprehensibly vast puzzle. And that's both humbling and exhilarating. But the search for evidence continues. Could we ever find direct proof of other universes? Or will they remain forever beyond our reach, hidden in the depths of an infinite multiverse? If parallel universes exist, how would we ever prove it? Scientists are exploring some of the most ancient clues in the cosmos remnants from the early universe itself to find answers. These observations might hold the key to unlocking the mystery of the multiverse. Let's start with the cosmic microwave background, or CMB. This faint glow of radiation is like a time capsule, a snapshot of the universe just 380,000 years after the Big Bang. It's the oldest light we can observe, and it holds a wealth of information about how our universe began. When scientists study the CMB, they look for patterns, subtle irregularities in this ancient light. These patterns tell us how matter was distributed in the early universe and how galaxies eventually formed. But here's the intriguing part. If our universe ever interacted with another universe, perhaps a neighboring bubble in the multiverse, it could have left a detectable mark in the CMB. Imagine two soap bubbles colliding. The point of contact creates a ripple. Similarly, a collision between universes might have left imprints in the fabric of space-time that we could still see today. So far, no conclusive evidence of such collisions has been found. But that hasn't stopped scientists from looking. Telescopes like the Planck satellite have mapped the CMB in exquisite detail, searching for anomalies that could hint at a multiverse. Another area of exploration comes from the distribution of matter in the universe. If parallel universes exist, they might subtly influence how galaxies are arranged on the largest scales. Some researchers have suggested that strange alignments or patterns in the cosmos could be the result of interactions with other universes. And then there's the concept of quantum fluctuations. These tiny variations in energy present during the inflationary period could have seeded the creation of not just galaxies, but entire universes. Observing these fluctuations and understanding their role might provide further clues about the multiverse. But here's the challenge: proving the existence of other universes is incredibly difficult. By definition, these universes exist outside our own, beyond the boundaries of what we can directly observe. It's like trying to see the other side of a wall when you're locked in a room. Still, the search continues. Scientists are pushing the limits of technology and theory, probing deeper into the origins of our universe. Every discovery brings us closer to understanding whether we're part of a multiverse or whether our universe stands alone in the vast expanse of reality. So could the answers be hidden in the light from the earliest moments of creation? Or will the multiverse remain forever, a tantalizing mystery, just out of reach? Now let's step away from the theories for a moment and dive into something more imaginative. What would it actually be like to live in a parallel universe? Could it feel similar to our own reality? Or would it be so different that we wouldn't even recognize it as life? Picture this. You wake up one morning in a parallel universe. At first glance, everything looks the same. The sky is blue, the trees sway in the wind, and the familiar buzz of life fills the air. But as you step outside, small details start to shift. Maybe the cars hover instead of drive. Perhaps the laws of physics allow people to float rather than walk. Or maybe history unfolded differently. Your city, your country, even your own life took a drastically different path. Now imagine another version, one where the differences are subtle. Maybe you're living the same life but with a few twists. You took a different career, married someone else, or pursued a long-forgotten dream. In a parallel universe, every decision, every chance encounter could lead to an entirely new reality. But what if the differences were more profound? In some universes, the laws of nature themselves could be entirely alien. Stars might never form. Planets might not exist. Time could flow backward, or gravity could be so weak that nothing holds together. Would such a universe even feel like reality to us? Here's a mind-bending thought. If we were to somehow find ourselves in a parallel universe, Would we even know our senses and brains are adapted to perceive the reality we live in? A universe with radically different laws of nature might be completely incomprehensible, like trying to imagine a color you've never seen. But the biggest question is perhaps this: in a world of infinite possibilities, how much would those differences actually matter? Would you still be you in another universe? Or would the subtle changes in your environment, your choices, and your circumstances create someone entirely new? Exploring what it's like to live in a parallel universe forces us to reflect on what defines reality and what defines us. Is it our surroundings, our experiences, or something deeper that transcends all possible worlds? And yet there's one more tantalizing question. If these universes are out there, could we ever visit them? Could we cross the boundaries of our reality and step into another? That's what we'll explore next. Now comes the big question. The one that feels like it's straight out of science fiction. Could we ever travel to other realities? Could we leave our universe and step into a parallel one? To answer that, we need to start by understanding the boundaries of our own universe. Right now, everything we know about space-time and matter suggests that our universe is a closed system. Like living inside a snow globe, we're confined to the dimensions and physical laws that define our reality. So the idea of breaking out and entering another universe seems impossible. But impossible is a word that science loves to challenge. Some theories suggest there might be loopholes in the fabric of space-time portals, if you will, that could allow travel between universes. Think of wormholes, those hypothetical tunnels connecting distant parts of space. Some scientists believe that if wormholes exist, they might also act as bridges between entirely different realities. Here's the catch. Wormholes, if they exist at all, would be incredibly unstable. The tiniest disturbance could cause them to collapse before anyone or anything could pass through. But what if we could stabilize one theoretically advanced civilizations far more advanced than ours might have the technology to harness wormholes as gateways to other universes? And then there's the idea of quantum entanglement, a strange phenomenon where two particles, no matter how far apart, are mysteriously connected. Some physicists speculate that this spooky action at a distance might hint at deeper connections between universes. Could quantum mechanics provide a roadmap for traveling between realities? Of course, there are massive challenges. Even if we discovered a way to reach another universe, we'd have no idea what conditions await us. Would it be safe? Would the laws of physics there even allow us to survive? Imagine stepping into a universe where gravity is so strong that you're instantly crushed, or so weak that atoms can't hold together. But there's another question, perhaps a more philosophical one. If we could travel to other realities, should we? What happens if we encounter another version of ourselves? What ethical dilemmas arise from meddling in a universe that isn't ours? For now, the idea of traveling to parallel universes remains a tantalizing dream, a frontier for future scientists and explorers to imagine. But even if we can't cross the boundaries of our reality, the very act of asking these questions pushes the limits of our understanding and inspires us to think beyond what we know. So will we ever build a bridge to another universe? Or will the multiverse remain forever out of reach, a world of infinite possibilities just beyond the edge of our imagination? Now let's confront one of the most profound questions about parallel universes. What happens if we interact with another version of ourselves? It's an idea that feels exciting and unsettling, all at once, raising ethical and philosophical dilemmas that challenge how we see ourselves and our place in reality. Imagine meeting another you, At first, it might feel like looking into a mirror, but this reflection isn't exact. Maybe they made different choices. Maybe they're living the life you always dreamed of or the one you've feared. How would that change the way you see yourself? Would you envy them, pity them, or would you feel a sense of connection knowing that their life could so easily have been yours? Here's the ethical dilemma. Would you have the right to influence their reality? If their life is better, would you try to learn from them, or even take their place? If it's worse, would you feel obligated to help them, even if it meant disrupting their world? And what about the consequences of your interaction? Think about the ripple effect. In your universe, every choice you make affects the people around you. But in a parallel universe, the stakes could be even higher. A small action, one conversation, one decision might radically alter an entire timeline. Then there's the question of identity. If there are infinite versions of you, is there such a thing as the real? Are you defined by your choices, your circumstances, or something deeper, something constant across all realities? This isn't just a philosophical exercise. It's a question that strikes at the core of how we understand ourselves. And finally, the most unsettling question of all, what if the other version of you is fundamentally different? What if they've made choices that you can't reconcile with choices that challenge your sense of morality or identity? Could you still see them as you? Or would they feel like a stranger? Interacting with another version of ourselves isn't just a fascinating what if. It forces us to confront the nature of free will morality and selfhood. It's a thought experiment that asks if we are one of infinite possibilities. How much of who we are is truly unique? Perhaps the ultimate ethical question is this: if we ever had the chance to step into another version of our life, would we take it? Or would the risks to ourselves, to others, and to reality itself be too great? The idea of parallel universes isn't just a scientific or philosophical concept. It's a profound challenge to how we perceive reality and our place within it. For centuries, humanity has sought to understand the cosmos, from ancient myths about the heavens to the modern equations of physics. We've long assumed that our universe is all there is, that everything we know and experience exists within this singular reality. But the possibility of parallel universes forces us to confront an unsettling truth. What if we're just a tiny piece of something infinitely larger? Think about it. If there are countless other universes, each with its own stars, galaxies, and perhaps even life, then our universe, our home, might not be as unique as we once thought. That realization can feel humbling, even disorienting. Are we just one story among billions playing out in an endless cosmic library? And what about you? If infinite versions of you exist, each shaped by slightly different choices or circumstances, then what defines your individuality? Are you truly unique, or just one expression of endless possibilities? This idea doesn't just challenge how we see ourselves, it also forces us to rethink humanity's place in the grand scheme of things. For generations, we've seen ourselves as the center of the story, the observers of the universe. But if the multiverse exists, then we're not the center at all. We're a single thread in a vast, intricate tapestry, woven alongside infinite others. But here's the paradox. While the concept of parallel universes can make us feel small, it can also inspire a profound sense of connection. If reality is infinite, then every choice, every possibility, every moment has value. It's a reminder that even in the vastness of the cosmos, our actions still matter because they're part of something much greater than ourselves. The idea of parallel universes isn't just about what's out there, it's about how we understand our place in it. Are we explorers seeking answers to the ultimate mysteries? Or are we simply participants in a story so vast and complex that we may never fully comprehend it? Either way, it's a journey that forces us to see reality and ourselves in a whole new light. The concept of parallel universes doesn't just expand our view of the cosmos. It directly challenges some of our most deeply held beliefs about free will fate and the nature of consciousness. Let's start with free will. We like to think of our choices as defining who we are. Every decision, big or small, feels like a unique thread in the fabric of our lives. But what if in the multiverse, every choice you could possibly make does happen? In one universe, you chose one path. In another, a completely different one. If every possibility is realized somewhere, then do you truly have free will? Or are you just playing out one version of an endless set of possibilities? Then there's fate. If parallel universes exist, does that mean everything is inevitable? If every outcome exists in some reality, then does it matter which choices you make? Or does the existence of infinite possibilities mean that no single outcome is destined? It's a paradox that forces us to rethink what it means to be in control of our lives, and whether the idea of control itself even makes sense in a multiverse. And what about consciousness? Who are you in the context of infinite versions of yourself? Is your consciousness unique to this universe? Or is it somehow connected to all your counterparts in other realities? Philosophers and scientists have long debated whether consciousness is a purely physical phenomenon or something more profound. The multiverse takes this debate to a new level. Could our minds, our very sense of self, be just one fragment of a larger interconnected whole? Here's a thought experiment. If you could observe every version of yourself across all universes, would you still feel like the same person? Or would the differences, subtle or dramatic, redefine your understanding of who you are? The idea of parallel universes doesn't just stretch the boundaries of science. It forces us to confront some of the most profound questions about existence itself. It challenges the very concepts of individuality, choice, and identity, leaving us to wonder in a reality of infinite possibilities. What does it truly mean to be? These are not easy questions to answer, but they remind us that exploring the multiverse isn't just a journey through space and time. It's a journey into the depths of our own understanding, one that may forever change the way we see ourselves and the universe around us. Parallel universes don't just challenge our understanding of reality, they open the door to entirely new realms of discovery. If even a fraction of the multiverse theories prove true, they could revolutionize the way we see the cosmos and our place within it. Imagine the possibilities. If we could uncover evidence of other universes, we might learn why our universe has the specific properties it does, why the laws of physics are fine-tuned to allow stars to form, planets to exist, and life to evolve. Perhaps in studying other realities, we'd find universes where the conditions are wildly different, teaching us more about the delicate balance that makes our own universe so special. And what about the origins of reality itself? Parallel universes could provide clues about how and why the universe began. Some scientists propose that studying the multiverse might reveal whether the Big Bang was a singular event or just one of countless beginnings in an endless cycle of cosmic creation. Then there's the technological potential. If we could somehow harness the principles of parallel universes, like the mysterious connections hinted at by quantum mechanics, imagine what might be possible. Could we use those principles to solve problems we've never been able to solve before, like faster-than-light travel, infinite energy sources, or even new ways to explore the cosmos? But perhaps the greatest discoveries would come not from the differences between universes, but from what they share. By studying the multiverse, we might uncover universal truths, patterns, or principles that apply across every reality. These insights could help us better understand the deepest questions about existence, why there is something rather than nothing, what consciousness truly is, and what the ultimate fate of reality might be. Of course, these discoveries are still far off, lying on the very edges of what we can imagine. But the potential is breathtaking. The multiverse, if real, doesn't just expand the cosmos. It expands the boundaries of human knowledge, inviting us to explore not just the universe we live in, but the infinite possibilities that lie beyond. Ultimately, the pursuit of understanding parallel universes isn't just about science, it's about curiosity. It's about the human drive to seek answers to the biggest questions, to push past the limits of what we know, and to embrace the unknown with open minds and boundless wonder. The discoveries we make might not just change what we know about the universe, they might change what we know about ourselves. The possibility of parallel universes is more than just a scientific theory or a philosophical idea. It's an invitation to expand our imagination and challenge the way we see reality. Few concepts are as captivating or thought-provoking, drawing us into questions that seem to stretch beyond the limits of what we can understand. If these universes exist, they offer a glimpse into infinite possibilities, worlds where history unfolded differently, where the laws of physics may not resemble our own, or where versions of ourselves are living lives we can only dream of. But even if parallel universes remain forever out of reach, the very act of exploring them forces us to think bigger, to ask questions that transcend the boundaries of science and philosophy. At its core, the idea of parallel universes reminds us of the vastness of reality. It's humbling to imagine that our universe might be just one small piece of an endless multiverse, and yet it's exhilarating to know that we're part of something so immense, so mysterious, and so beautiful. And perhaps whether or not we ever find proof of other realities, the most important discovery might be what this exploration teaches us about ourselves, about our place in the cosmos, about the choices we make, and about the boundless curiosity that drives us to keep asking, keep searching, and keep wondering. So as we close this journey, consider this in a universe so full of mystery, where every possibility could exist somewhere. What does that mean for the choices you make today? What does it mean for how you see yourself, your world, and the infinite unknown? The answers may lie beyond our reach, but the questions will always push us forward. So as you step back into your own universe, carry this thought with you. Every question we ask, every possibility we imagine, brings us closer to understanding the extraordinary reality we call home. And who knows? Perhaps somewhere in another reality, another version of you is asking these very same questions, dreaming, exploring, and seeking answers in their own way.
Does reality truly exist if no one is observing it? How can two particles on opposite sides of the universe instantly influence each other? Is it possible that every decision we make creates a parallel universe? If time can reverse at the quantum level, what does that mean for our future? Could the human brain operate like a quantum computer? Are we living in a reality where everything is invisibly interconnected? Welcome to the perplexing world of quantum mechanics, where the rules we think govern reality break down, and the universe reveals itself as something far stranger than our everyday experience suggests. The mysterious truths of quantum mechanics. Imagine tossing a pebble into a pond. The ripples spread out, graceful and predictable. Now, what if the pebble could behave both like a ripple and as a solid object at the same time? Quantum mechanics is a branch of physics that studies the smallest building blocks of the universe, particles like electrons, photons, and quarks. Yet the more we look, the less solid reality seems to become. This section will explore three of its most mysterious phenomena: wave-particle duality, superposition, and quantum entanglement. Wave-particle duality is the idea that light and matter can behave both as particles and waves, depending on how they're observed. Imagine asking someone whether a coin is heads or tails, and their answer changes depending on how closely you're looking. The double-slit experiment. In this iconic experiment, scientists shot particles, like electrons or photons, at a barrier with two slits. Behind the barrier was a screen to capture where the particles landed. Step 1. When the particles were observed closely, they behaved like tiny marbles, forming two distinct lines on the screen, one behind each slit. Step 2. When not observed, the particles acted like waves, spreading out and forming an interference pattern of many lines, as though the particles had passed through both slits simultaneously and interfered with themselves. Simplified explanation: think of a particle as a traveler facing a fork in the road. When no one is watching, the traveler takes both paths at once, exploring every possibility. But the moment you watch, the traveler chooses one path, as if responding to your gaze. Why it's strange? This suggests that the mere act of observing can change the fundamental behavior of matter. Is reality shaped by observation? And if so, what does that mean about the universe when no one's watching? Quantum superposition. In classical physics, an object is either here or there, in one state or another. Quantum mechanics introduces superposition, where particles exist in multiple states simultaneously until measured. Schrödinger's cat thought experiment. A physicist, Erwin Schrödinger, imagined placing a cat in a box with a vial of poison, which would break if triggered by a random quantum event. Until someone opens the box, the cat exists in a superposition of states both alive and dead. Imagine flipping a coin and sealing it inside an envelope. To you, the coin is both heads and tails at the same time, because you haven't seen it yet. It's only when you open the envelope that the coin chooses a side. Why it's strange, superposition challenges the idea of objective reality. If particles exist in multiple states until observed, is the universe inherently uncertain? And how does reality decide which state to take when observed? Quantum entanglement. Entanglement occurs when two particles become so deeply connected that the state of one instantly determines the state of the other, no matter how far apart they are, even if they're on opposite sides of the universe. Einstein's skepticism. Albert Einstein famously called entanglement spooky action at a distance, because it seemed to defy the speed of light, the universal speed limit. Yet experiments have repeatedly confirmed this phenomenon. Simplified metaphor: imagine you have a pair of gloves. You send one glove to the moon and keep the other on Earth. Without looking, you don't know which is the left glove and which is the right. The moment you check the glove on Earth and see it's the left one, you instantly know the glove on the moon is the right, even though no information traveled between them. Entanglement suggests that particles can remain connected in a way that transcends space and time. Could this imply a deeper, hidden layer of reality where everything is interconnected? Questions to ponder. If observing particles changes their behavior, does that make us co-creators of reality? How can particles influence each other instantaneously across vast distances? Is the universe fundamentally random? Or is there an underlying order beneath the quantum chaos? Quantum mechanics challenges our deepest assumptions about reality. Wave-particle duality blurs the lines between objects and actions. Superposition raises questions about the nature of existence, and entanglement hints at a universe where everything is interconnected in ways we're only beginning to grasp. This is just the beginning of our journey into quantum science. As we dive deeper, these mysteries will intertwine with questions of philosophy, consciousness, and the very fabric of time. But for now, quantum mechanics reminds us of a humbling truth: the universe is far stranger and far more wonderful than we ever imagined. Philosophy and quantum mechanics. Quantum mechanics doesn't just alter our understanding of physics, it challenges our fundamental beliefs about reality, existence, and the nature of the universe. It brings us face to face with questions that philosophers have grappled with for centuries. Could quantum mechanics provide the missing link between science and philosophy? In this section, we explore the fascinating relationship between quantum theory and philosophical inquiry. The observer effect. Does reality exist without observation? The observer effect in quantum mechanics suggests that the mere act of observing a quantum system can change its behavior. In the famous double-slit experiment mentioned earlier, particles like electrons or photons behave as waves when unobserved, and as particles when observed. But here's the philosophical twist. If observation affects reality, then can we really say that the world exists independently of us? Does the universe only decide its state when we look at it? This is a powerful philosophical question that echoes the debate about whether existence requires a mind to perceive it. Simplified explanation. Imagine you're trying to catch a butterfly in the wild. Every time you approach it, the butterfly flutters away, changing its position and behavior. If you stand still and don't try to catch it, the butterfly behaves in its natural way. The act of trying to catch it or observe it changes what it does. This is like what happens at the quantum level. Our attempt to measure something changes its state. Philosophical connection. This idea mirrors solipsism, a philosophical theory that suggests only the mind of the observer can be known to exist. In quantum mechanics, it's almost as if reality isn't truly there until we observe it. Could our minds actually be shaping the world around us? If so, what does that say about free will and our place in the universe? Questions to ponder. If the act of observing creates reality, what does that say about the world when we're not looking? Can we ever truly know the universe if our perception of it always shapes it? The multiverse hypothesis, a universe for every possibility. Quantum mechanics also suggests that, when faced with multiple possible outcomes, particles don't just pick one, they exist in all possibilities simultaneously until measured. This leads to the many worlds interpretation, which proposes that every time a quantum event occurs with multiple possibilities, the universe splits into separate branches, each representing one of the possible outcomes. Essentially, every decision, every quantum event creates a new universe. Simplified explanation. Imagine you have a coin and you're about to flip it. In the quantum world, the coin doesn't just land on heads or tails, it lands on both, in separate worlds. In one universe, it's heads, in another, it's tails. Every possible outcome of every quantum event exists in its own parallel universe. This theory raises the idea of determinism versus free will. If every possible outcome exists in a parallel universe, does that mean we're simply along for the ride, with no true choice? Or does the fact that we experience one outcome imply that we are actively shaping our reality? Questions to ponder. If there are infinite universes, does it mean all possibilities are actualized, or is there still a guiding hand behind it all? What does this say about the role of free will in our lives? Are we simply living out one branch of the many possibilities? Determinism versus free will. Does the quantum world allow for both? In classical physics, the universe was thought to be deterministic. Everything happens because of prior causes, like the turning of a clock. But quantum mechanics doesn't fit this model. Quantum mechanics tells us that at the microscopic level, events are not entirely predictable and chance plays a significant role. This creates an interesting paradox when thinking about human behavior. Is everything determined by the laws of physics, or do we have the power to make choices that aren't preordained? Think of a rolling dice. Classical physics would say the dice's outcome is determined by its starting position, how fast it rolls, and all the forces acting on it. But in quantum mechanics, the dice could land on several faces at once, and it's only when we look at it that we see which face it lands on. Could our decisions be more like this quantum roll of the dice? This aligns with a long-standing philosophical debate. Is our universe deterministic, where everything happens for a reason, or is there room for randomness and free will? Quantum mechanics, with its inherent unpredictability, seems to suggest that randomness plays a role in shaping our world. But what does that mean for the human experience of choice? Questions to ponder. If quantum mechanics allows for randomness, does that free us from being controlled by the laws of physics, or does it create a different kind of order? How does this randomness relate to the concept of free will? If we're free to choose, is it random, or is there a deeper purpose behind our decisions? In this section, we've explored how quantum mechanics doesn't just change our view of the universe, it compels us to revisit age-old philosophical questions. From the observer effect's challenge to objective reality, to the multiverse's implications for free will, quantum theory forces us to reconsider what we think we know about existence. Quantum mechanics isn't just a tool for physicists, it's a bridge between science and philosophy, urging us to ask deeper questions about the nature of reality, consciousness, and choice. As we continue to explore these ideas, we'll see how quantum mechanics intertwines not only with the smallest particles, but also with the deepest questions about our place in the cosmos. Quantum mechanics and consciousness. The intersection between quantum mechanics and consciousness is one of the most intriguing and speculative areas in modern science. Does quantum theory hold the key to understanding consciousness? Could our minds be operating on quantum principles, giving rise to thoughts, emotions, and self-awareness? This section explores how quantum mechanics might be connected to the very nature of consciousness, blurring the lines between physics, philosophy, and psychology. Quantum brain hypothesis. Could the brain work like a quantum computer? One fascinating theory is that the brain could operate like a quantum computer, using the principles of superposition and entanglement to process information in ways classical computers can. The idea is that quantum effects might be occurring within our neurons, influencing how we think, perceive, and experience the world. Imagine trying to solve a puzzle by checking all the possible answers one at a time. A classical computer would do this in a linear fashion, one possibility after another. But a quantum computer, using superposition, could check all possibilities at once much faster. If our brains worked this way, it could explain the speed and complexity of human cognition. Supporting evidence. Some scientists point to microtubules, tiny structures within our neurons, as potential quantum processors. These microtubules might be able to support quantum states, which could allow the brain to process vast amounts of information at incredible speed. The hypothesis was notably proposed by physicist Roger Penrose and anesthesiologist Stuart Hameroff in their theory of orchestrated objective reduction, which suggests that consciousness arises from quantum processes within the brain. Why it's fascinating? If the brain operates on quantum principles, it would mean that our minds could be far more complex than we currently understand. It might also explain the subjective quality of consciousness, why we experience thoughts and emotions rather than simply processing information like a computer. Questions to ponder. If quantum mechanics is involved in consciousness, could we ever fully understand how thoughts arise? Could quantum processes help explain the hard problem of consciousness? Why subjective experience arises from objective brain activity? Panpsychism and quantum physics, consciousness in every particle. Panpsychism is the philosophical theory that consciousness is a fundamental property of all matter. In other words, everything down to the tiniest particle has some degree of consciousness. Some proponents of this view argue that quantum mechanics could provide the framework for understanding how consciousness pervades the universe. Simplified explanation. Imagine you have a drop of water. In classical physics, you could describe it purely by its physical properties, its weight, its temperature, etc. But what if, on a deeper level, the molecules inside the water also had an awareness of their environment? Panpsychism suggests that consciousness isn't limited to humans or animals. Instead, it's a fundamental feature of the universe. Quantum connection. Quantum mechanics hints at the idea that consciousness could be an intrinsic feature of matter. For example, quantum coherence, the ability of particles to remain in a superposition of states, could be the physical manifestation of a deeper, universal consciousness. This idea aligns with David Bohm's theory of the implicate order, which suggests that everything in the universe is interconnected through a deeper layer of reality that could also involve consciousness. Why it's fascinating? If consciousness is embedded in the very fabric of matter, it suggests that the universe itself could be conscious. In this view, every atom, every photon, and every quark might have a tiny, rudimentary form of awareness. This could radically change how we think about the mind-body problem and our relationship with the universe. Questions to ponder. If every particle has consciousness, does that mean we are connected to everything around us in a profound way? Could quantum processes in particles explain the nature of subjective experience? Integrated Information Theory, IIT. Could the universe itself be conscious? One of the most ambitious theories of consciousness is integrated information theory, developed by neuroscientist Giulio Tononi. IIT proposes that consciousness arises from the degree to which a system can integrate information. The more interconnected and integrated the system, the more conscious it is. This theory suggests that consciousness might not be limited to humans or animals, but could be a property of any system that integrates information in a sufficiently complex way. Think of a light bulb. When it's on, it illuminates the room, but when you turn off the switch, the light goes out. In a way, the light bulb integrates the flow of electricity, but it's not conscious. Now, imagine a more complex system, like the brain, which integrates vast amounts of information across billions of neurons. According to IIT, the more information that's integrated, the higher the level of consciousness. Quantum connection. If IIT is correct, and consciousness is about integrating information, then quantum mechanics could play a key role. Quantum coherence, the ability of quantum systems to remain in a state of superposition and interact with one another, might allow for a higher level of information integration. In this way, the quantum world might help explain the emergence of consciousness in complex systems. IIT could provide a framework for understanding not only human consciousness, but also the consciousness of the universe itself. If the universe is a vast network of interconnected systems, each integrating information in complex ways, could it be that the universe itself has some form of awareness? Questions to ponder. If IIT is correct, could the universe be conscious in the same way that our brains are conscious? What would it mean if the universe as a whole had an awareness of its own existence? In this section, we've explored how quantum mechanics could be linked to consciousness, offering new possibilities for understanding the mind. From the idea of the brain operating as a quantum computer, to the radical suggestion that consciousness may be a fundamental property of matter, quantum theory opens up new avenues for thinking about awareness and existence. Quantum mechanics, with its strange and counterintuitive properties, challenges our understanding of reality, and in doing so, it may be pointing us toward a deeper, more interconnected view of consciousness. If consciousness arises from quantum processes, the universe might be far more conscious than we ever imagined, perhaps even in ways we are yet to comprehend. Quantum mechanics and time. Time is something we all experience, seconds ticking by, days passing, and memories fading as the years go on. But quantum mechanics suggests that time might not be as straightforward as we think. In fact, quantum theory challenges our most basic understanding of time, raising deep philosophical questions about its true nature. Could time be more fluid than we've ever imagined? Is it a fundamental part of the universe, or could it be an illusion? In this section, we'll explore how quantum mechanics reshapes our concept of time and what it means for our understanding of the universe. Non-linearity of time. Does time flow in one direction? In classical physics, time flows in one direction from the past to the future. This idea is deeply rooted in the second law of thermodynamics, which states that entropy, or disorder, tends to increase over time, creating a natural arrow of time that moves forward. However, quantum mechanics presents a different picture. At the quantum level, time may not flow in a strict, linear fashion. Imagine you're watching a movie. As the story progresses, things happen in sequence, first this, then that. But at the quantum level, the sequence of events might not always be fixed. It's as though you're watching a movie where the scenes could play in any order, and the story might change depending on your perspective or how you're observing it. Time itself could be much more flexible than we experience it in our daily lives. Why it's strange, in quantum mechanics, particles don't always behave as though they follow a strict timeline. For instance, certain quantum processes can seem to reverse time, where particles appear to go backward in time, which challenges the idea of a universally directed flow of time. Quantum mechanics example. Quantum particles can travel backward in time according to the Feynman diagrams in quantum field theory. These diagrams depict particles as traveling through both forward and backward directions in time, essentially reversing the arrow of time under certain conditions. Questions to ponder. If time can flow backward at the quantum level, what does that say about our perception of the past, present, and future? Could the experience of time we have in our everyday lives be an illusion, a consequence of our limited perspective? Time reversal symmetry. Could time run backward? One of the most mind-bending implications of quantum mechanics is the idea of time reversal symmetry. This principle suggests that the laws of physics are the same whether time flows forward or backward. If you could rewind a quantum process, the physics would work just as they did going forward. In other words, if you could reverse the motion of a quantum system, it wouldn't violate any physical laws. Think of a video of a ball bouncing. If you play it backward, the ball seems to jump up from the floor, defying gravity. But in the quantum world, the ball's behavior would not change if played backward. The particles and forces involved would still obey the same fundamental rules, whether time is moving forward or backward. Why it's strange, time reversal symmetry in quantum mechanics challenges our everyday experience. We never see time rewinding in the macroscopic world. We observe things breaking, aging, and decaying in one direction only, forward. Yet, at the quantum level, particles behave as though they could reverse direction, suggesting time itself may be a construct based on our perception. At the subatomic level, certain particles, like photons and electrons, behave symmetrically under time reversal. If you were to reverse the direction of time for a quantum event, the system would evolve in precisely the same way, leading scientists to wonder if time's flow is an artifact of our observations. Questions to ponder. If time is reversible at the quantum level, does that mean our concept of time itself is just a mental construct? Could this symmetry have real-world consequences, such as in the development of time travel technologies? Quantum time travel. Is time travel possible? Could quantum mechanics make time travel possible? While time travel has long been a staple of science fiction, quantum mechanics opens the door to a theoretical possibility. The strange behaviors of particles at the quantum level, like superposition and entanglement, suggest that time may be more flexible than we realize. Could we, in theory, travel backward or forward in time? Simplified explanation. Imagine you're standing at a fork in the road, and both paths lead to the same destination. In classical physics, you can only take one path. But in the quantum world, there's a chance both paths are traveled simultaneously, with each one existing in a different timeline. It's as if you're living in two parallel realities, one where you choose one path, and another where you take the other. While actual time travel is still the stuff of fiction, some theoretical physicists suggest that quantum mechanics could allow us to move through time in ways we can't fully comprehend yet. One of the key ideas here is wormholes, theoretical shortcuts in space-time that could allow travel between different points in time and space. Quantum mechanics example. A specific type of quantum phenomenon called closed time-like curve suggests that time loops where the future influences the past could exist within the framework of general relativity. These theoretical time loops have been studied in the context of quantum particles, and they might be the key to understanding time travel. Questions to ponder. If quantum mechanics allows for time loops, could we travel back to the past and change history? What would happen to the laws of causality if time travel were possible? Quantum mechanics fundamentally challenges our understanding of time. From non-linearity to time reversal symmetry and the possibility of time travel, quantum theory presents a view of time that's far from the fixed, unidirectional flow we experience in our daily lives. At the quantum level, time is not an absolute, steady force, it's a malleable, fluid aspect of the universe. As we continue to explore the relationship between quantum mechanics and time, we may find that our perception of reality itself is shaped by deeper, quantum-level processes. Perhaps in time, the mysteries of time travel, time reversal, and the true nature of temporal flow will be unraveled, giving us an entirely new perspective on our place in the universe. The future of quantum science. Quantum mechanics isn't just about understanding the fundamental nature of reality, it's driving the next technological revolution. While we've already explored some of the mind-bending concepts that quantum mechanics presents, its potential applications in the future could change everything from how we compute to how we communicate. This section explores the cutting-edge developments in quantum science and what they might mean for the future of humanity. Quantum computing, the next leap in technology. Quantum computing harnesses the strange properties of quantum mechanics, such as superposition and entanglement, to solve problems that classical computers simply cannot. Unlike classical computers, which process information as bits, either 0 or 1, quantum computers use quantum bits or qubits, which can represent both 0 and 1 at the same time due to superposition. This gives quantum computers the ability to perform many calculations simultaneously, opening up possibilities for solving complex problems in seconds that would take classical computers millennia. Think of a classical computer like a person who can only check one box at a time on a list. A quantum computer, on the other hand, can check all the boxes at once, dramatically speeding up problem-solving processes. Quantum computers could revolutionize fields like cryptography, material science, drug discovery, and more. Problems that are currently intractable, such as simulating molecules for new drug compounds or optimizing complex systems, could soon be solved by quantum computers. Example, Google's Sycamore quantum processor achieved quantum supremacy in 2019 by solving a problem that would have taken the world's most powerful classical computer 10,000 years to solve within just 200 seconds. This marked a significant milestone in demonstrating the real-world potential of quantum computing. Questions to ponder. How soon will quantum computers be able to solve practical problems we cannot yet imagine? What ethical implications could arise as quantum computing accelerates developments in fields like artificial intelligence and cryptography? Quantum cryptography, the future of secure communication. Quantum cryptography uses the principles of quantum mechanics to create secure communication channels that are theoretically impossible to hack. The most famous application of quantum cryptography is quantum key distribution (QKD), which allows two parties to exchange encryption keys securely. If anyone tries to intercept the communication, the quantum system detects the intrusion and changes the key, rendering the hack useless. Simplified explanation: imagine sending a secret message inside a sealed envelope. In classical systems, if someone intercepts the envelope, they can open it and read the message. In quantum systems, if anyone tries to open the envelope, the quantum properties ensure that the contents are changed, making it obvious that someone was tampering with the message. Quantum cryptography could lead to virtually unbreakable security systems. Governments, banks, and organizations could use QKD to ensure that sensitive data remains protected from hackers and cyber threats, even in a future where supercomputers could break current encryption methods. Example, in 2017, China launched the world's first quantum satellite, which successfully demonstrated the use of QKD to establish secure communications between ground stations. This marked a significant step toward the global deployment of quantum communication systems. Questions to ponder. How will quantum cryptography change the way we think about privacy and security in the digital age? Could quantum communication lead to a new era of trust and transparency in global systems? Quantum sensors, revolutionizing measurement and detection. Quantum sensors leverage the unique properties of quantum systems to make incredibly precise measurements that classical sensors cannot achieve. These sensors can detect incredibly small changes in magnetic fields, gravitational waves, and even time. They hold the potential to revolutionize fields like navigation, geology, and medical diagnostics. Imagine you're trying to measure the tiniest vibrations on a surface. A classical sensor might miss the smallest signals, but a quantum sensor, like a super-sensitive microphone, can pick up every detail no matter how small. This precision opens up entirely new possibilities for measuring forces in the universe. Quantum sensors could allow for GPS-independent navigation, where extremely precise measurements of gravitational fields can track positions without relying on satellites. Additionally, quantum sensors could lead to breakthroughs in medical imaging, allowing for earlier detection of diseases or abnormalities on a molecular level. Example, quantum gravimeters are already being used to measure the Earth's gravity with extreme precision. This could help scientists detect underground resources, map geological structures, or even monitor natural disasters like earthquakes and volcanic eruptions in real time. Quantum energy, harnessing the power of the quantum world. One of the most ambitious goals of quantum science is to harness quantum effects to create more efficient energy systems. For example, quantum mechanics could play a role in developing quantum batteries or improving solar panels by using quantum properties to capture more light and convert it into energy. Simplified explanation: imagine a solar panel that works like a sponge, absorbing as much sunlight as possible. Using quantum mechanics, we could make the sponge much more efficient, allowing it to soak up more light and convert it into usable energy. Example, researchers are already experimenting with quantum dots, tiny semiconductor particles that can capture sunlight at higher efficiency than traditional solar cells. These breakthroughs could help make renewable energy more efficient and affordable, accelerating the shift to cleaner energy sources. Questions to ponder. Could quantum energy solutions help us tackle the global energy crisis? How soon could quantum energy technologies become commercially viable, and what impact will they have on the environment? Quantum science is not just a theoretical pursuit, it's the gateway to a new technological era. From quantum computing and cryptography to the development of ultra-sensitive quantum sensors and more efficient energy systems, quantum mechanics holds the potential to revolutionize how we live, work, and interact with the world. While these technologies are still in the early stages of development, they're already showing promise. As we continue to unlock the secrets of the quantum world, we may find ourselves on the cusp of breakthroughs that will shape the future in ways we can't yet fully imagine. Real-world applications of quantum mechanics. Quantum mechanics, with its strange and fascinating properties, is not just a theoretical framework, it's already making an impact in the real world. While much of quantum physics seems abstract and theoretical, its principles are increasingly being applied to solve practical problems. From revolutionizing medical technologies to transforming how we navigate and communicate, quantum mechanics is paving the way for groundbreaking innovations that could change the way we live. In this section, we'll explore some of the most promising real-world applications of quantum mechanics and how they're already shaping industries and research. Quantum medical imaging, a new frontier in diagnostics. Quantum mechanics is starting to make its mark in the medical field, particularly in medical imaging. Quantum technologies, such as quantum sensors, can provide unprecedented sensitivity in detecting tiny changes in biological systems. This could lead to more accurate and earlier detection of diseases like cancer, neurological disorders, and heart disease, potentially saving lives by spotting issues before they become critical. Simplified explanation. Imagine you're using a flashlight to find something in a dark room. A regular flashlight gives you a basic view, but a quantum-enhanced flashlight would shine far brighter and reveal even the smallest details, allowing you to spot objects in the room with incredible precision. In medical imaging, quantum-enhanced tools could detect even the faintest changes in the body. Quantum sensors could make medical imaging more sensitive and accurate, enabling doctors to detect problems at earlier stages when treatment is more effective. For example, quantum imaging could help in detecting early-stage cancer, monitoring brain activity, or tracking the effectiveness of treatments for chronic conditions like Alzheimer's disease. One promising development is the use of quantum magnetometry, which can measure magnetic fields with extreme precision. This could help detect the subtle changes in the brain's magnetic field that may indicate neurological disorders or even predict seizures in epileptic patients. Questions to ponder. How could quantum-enhanced medical tools change the way doctors diagnose and treat diseases? What impact could early detection of conditions like cancer have on survival rates? Quantum energy solutions, harnessing the power of the quantum world. Quantum mechanics could play a key role in solving one of the world's most pressing issues: energy. By exploiting quantum effects, scientists aim to create quantum batteries and improve solar energy systems, making them vastly more efficient than current technologies. Imagine a super-efficient battery that can store more energy, last longer, and charge faster than anything we have today. Quantum mechanics might unlock the secrets to building such batteries, revolutionizing energy storage and making renewable energy sources, like solar and wind, more reliable and accessible. Quantum-based energy systems could lead to advances in energy storage, energy generation, and transmission, addressing the challenges posed by renewable energy and the increasing demand for power in a growing world population. Quantum technologies could enable smarter energy grids that optimize the distribution of power, potentially solving some of the biggest energy problems. Researchers are working on quantum dot solar cells, tiny particles that can absorb light more efficiently than traditional solar panels. Quantum dots could allow solar panels to capture more light, turning more of it into usable energy, which would make solar power far more efficient and cost-effective. Questions to ponder. Could quantum energy breakthroughs make renewable energy more reliable and sustainable? How soon could quantum energy solutions be available to the general public, and what would their impact be on the global energy landscape? Quantum navigation, beyond GPS and the digital revolution. Quantum mechanics is also revolutionizing how we navigate the world. Quantum sensors are already being used to create GPS-independent navigation systems. These quantum sensors can detect incredibly subtle changes in gravitational and magnetic fields, enabling highly precise positioning without relying on satellite signals. Traditional GPS relies on satellites orbiting the Earth to pinpoint your location. But quantum navigation systems could use ultra-sensitive quantum sensors to detect the Earth's natural magnetic fields and gravitational pull, allowing you to navigate with pinpoint accuracy whether you're in a dense forest, a submarine, or on another planet. Quantum-based navigation systems could eliminate the need for GPS satellites, which are vulnerable to interference and hacking. They could also enable high-precision navigation in places where GPS signals are weak or unavailable, like deep underground, underwater, or in space. Quantum gyroscopes, which use quantum entanglement and superposition to detect the rotation of objects, could be used to create extremely accurate navigation systems. These gyroscopes are already being tested in aerospace and defense applications, but their potential for everyday use, like in autonomous vehicles or deep-sea exploration, is enormous. Quantum computing in cryptography, the dawn of unbreakable security. Quantum computing is poised to revolutionize cryptography by providing the means to create encryption systems that are theoretically unbreakable. Traditional encryption methods could become obsolete as quantum computers gain the ability to break them, but quantum cryptography offers a solution by using the principles of quantum mechanics to secure data in ways that classical systems can't match. Current encryption relies on complex mathematical problems that are difficult for classical computers to solve. But quantum computers can solve these problems much faster. On the other hand, quantum cryptography ensures that any attempt to intercept or tamper with encrypted messages would be immediately detectable, making hacking virtually impossible. As cyber attacks become more sophisticated, quantum cryptography could offer a future-proof solution. It promises to secure everything from personal communications to banking transactions to national defense secrets without the risk of being hacked by even the most powerful computers. Example: in 2020, China's MISHIS satellite successfully transmitted quantum encrypted data across thousands of miles, demonstrating the potential for secure global communication using quantum technologies. Questions to ponder. What impact will quantum cryptography have on online privacy and security? Could quantum encryption help protect sensitive data from cyber attacks in the digital age? As we've seen, the real-world applications of quantum mechanics are not confined to theoretical physics. Labs, they are already shaping industries, technologies, and even our daily lives. From revolutionary medical imaging and energy solutions to quantum navigation and unbreakable cryptography, quantum mechanics is poised to transform every aspect of society. The future is quantum, and as we continue to unlock the mysteries of the quantum world, the possibilities are endless. Whether in health, energy, security, or computing, quantum mechanics promises a future where science fiction becomes science fact. As we continue to explore and harness these extraordinary technologies, we may be on the brink of a new era of innovation that will change the world forever. The quantum journey ahead. Quantum mechanics has taken us on a journey through the very fabric of reality itself, a realm where the familiar laws of physics are challenged and the impossible becomes possible. From the mind-bending properties of wave-particle duality to the profound questions it raises about time, consciousness, and our understanding of existence, quantum science pushes the boundaries of human knowledge and invites us to think in ways we never have before. We've explored how quantum mechanics is reshaping not only physics but philosophy, asking whether reality exists only when observed, and whether every possible choice creates a new universe. We've delved into the potential connections between quantum processes and consciousness, raising the possibility that the universe itself could possess a form of awareness. We've seen that quantum mechanics isn't just abstract theory, it's already changing the world in concrete ways. Quantum computing promises to revolutionize industries by solving problems that are currently beyond our reach. Quantum cryptography is set to make communication more secure than ever before. Quantum sensors and energy solutions could transform healthcare, navigation, and our global energy systems. The future of quantum science is a thrilling one. While there is still much to learn, the breakthroughs we've discussed could reshape entire industries, solve some of the world's most pressing problems, and open up new frontiers in technology and human potential. As quantum technologies continue to evolve, we are standing on the brink of a new era, an era where the strange, wonderful, and mysterious world of quantum mechanics becomes an integral part of our everyday lives. But perhaps the most important takeaway is this: quantum mechanics teaches us that the universe is far more interconnected, unpredictable, and beautiful than we ever imagined. Whether we're trying to unlock the secrets of consciousness or exploring new technologies, quantum science reminds us that there is still so much more to discover. We are only beginning to scratch the surface, and the future holds infinite possibilities. What if we could trace the origins of life itself? Why does the cosmos seem so perfectly tuned? Is the universe hiding its creator? Could the universe be alive? Is life a cosmic accident or a destined event? Are we truly alone in the universe? What if we could trace the origins of life itself? Is life on Earth a fleeting accident in an otherwise indifferent cosmos? Or is it a necessity written into the very fabric of the universe? Perhaps, even more astonishingly, could it be the deliberate creation of a higher intelligence? These questions have fascinated thinkers, scientists, and philosophers for centuries, pushing the boundaries of human imagination. The mystery of how life began is one of the deepest questions humanity has ever pondered. Despite centuries of progress in science and technology, the origins of life remain shrouded in uncertainty, leaving us to speculate at the intersection of science, philosophy, and even metaphysics. From the chaotic dance of atoms billions of years ago to the emergence of complex, sentient beings, the journey of life has ignited debates across disciplines. Is our existence the result of sheer chance, inevitable under universal laws, or the product of a higher, intentional design? Each perspective offers a unique lens, but none can yet claim to hold the definitive answer. This exploration will journey through three primary perspectives: the hypothesis that life arose by coincidence, the argument that life was an inevitable outcome of nature's laws, and the possibility that a higher consciousness designed the conditions for life to emerge. Through these lenses, we'll uncover the profound implications of each theory, examining evidence, raising questions, and contemplating what it all means for our understanding of existence. Coincidence, the role of randomness in life's origins. Life, in this view, is nothing more than a fortunate accident, a consequence of countless random interactions occurring under the right conditions. Imagine a chaotic primordial Earth, its surface bombarded by meteors, its atmosphere thick with gases, and its oceans bubbling with chemicals. Amid this seemingly anarchic environment, molecules collided, bonded, and eventually formed the building blocks of life. This hypothesis suggests that life is not guaranteed, but rather the result of an almost miraculous convergence of circumstances. It argues that, given the vastness of time and space, such a cosmic accident was bound to occur somewhere. Earth just happened to be the lucky winner in the lottery of existence. Abiogenesis, the scientific explanation for life's origins, posits that life arose naturally from non-living chemical compounds. This theory gained traction with the famous Miller-Urey experiment in 1953. In a controlled laboratory setup simulating early Earth's conditions, researchers exposed a mixture of water, methane, ammonia, and hydrogen to electric sparks, mimicking lightning. Remarkably, the experiment produced amino acids, organic compounds essential for life. The results were groundbreaking, proving that complex molecules could form spontaneously under the right conditions. Subsequent research has expanded on these findings, identifying potential pathways through which simple molecules could organize into self-replicating systems, the precursors to life. However, abiogenesis faces significant challenges. Critics point out that forming life's essential components, like proteins or RNA, is far more complex than creating amino acids. Even under ideal conditions, the probability of assembling functional proteins by chance is astronomically low, leading skeptics to question whether randomness alone could account for the emergence of life. Let's consider the staggering odds involved in life's emergence. The chance of a single functional protein forming spontaneously has been compared to a monkey typing out Shakespeare's Hamlet by randomly hitting keys on a keyboard. Now multiply that improbability by the complexity of an entire living cell. Scientists estimate that Earth existed for approximately 1 billion years before life emerged. While this time frame provides countless opportunities for chemical interactions, it also underscores how rare and extraordinary the conditions must have been for life to begin. The coincidence hypothesis raises a critical question. If life is a rare accident, why does the universe appear so finely tuned to allow it? For instance, the Earth orbits in the Goldilocks zone, where temperatures are just right for liquid water, a key ingredient for life. Some argue that this perfect alignment is too precise to be purely coincidental. Others counter that the universe's vastness ensures some planets would inevitably meet these conditions. To grasp this perspective, think of the universe as a vast casino, and Earth's origins as a game of roulette. The odds of life forming may have been infinitesimally small, but the wheel spun countless times across the cosmos. Earth, it seems, was the one lucky spin where the ball landed perfectly. The hypothesis that life arose by coincidence paints a picture of a fragile, improbable event in the grand chaos of the universe. Yet, this perspective also leaves us with a profound sense of uncertainty. If life truly is a cosmic accident, what does that say about its meaning or lack thereof? Necessity. Life is an inevitable outcome. Unlike the randomness of the coincidence perspective, the necessity hypothesis suggests that life was bound to happen. It argues that the physical and chemical laws governing the universe naturally lead to the emergence of life when conditions align. In this view, life is not a miraculous anomaly, but an inherent outcome of the universe's design, a natural expression of its potential. Imagine the universe as a carefully arranged orchestra. Every instrument, from gravity to electromagnetism, plays its role, creating conditions that make life not only possible but unavoidable. Life's building blocks rely on universal principles that drive molecules to organize into more complex forms. Consider the following: the Goldilocks zone. Earth orbits the Sun at just the right distance, allowing liquid water to exist, a critical factor for life. Many other planets in the universe may share similar conditions, suggesting that life could arise wherever these just right circumstances occur. Self-organization in chemistry. Certain molecules have an innate tendency to self-organize. For example, phospholipids spontaneously form membranes in water, mimicking the cell walls of living organisms. This self-assembly hints that life's essential structures could arise naturally under the right conditions. This perspective gains further support from extremophile organisms that thrive in extreme environments. From hydrothermal vents deep in the ocean to boiling acid springs, life has demonstrated its remarkable ability to emerge and survive in diverse conditions, reinforcing the idea that it may naturally arise wherever it can. The idea that specific chemical reactions, under specific conditions, inevitably lead to life. For instance, amino acids tend to link together when exposed to certain environmental pressures, potentially forming proteins over time. The role of water and carbon. Water's unique properties, like its ability to dissolve a wide range of substances, make it a crucial solvent for biochemical reactions. Similarly, carbon's versatility allows it to form complex molecules, such as DNA and proteins, making it the backbone of all known life. Astrobiological discoveries. Recent discoveries of organic compounds on comets and meteorites suggest that the building blocks of life are not unique to Earth. These findings bolster the argument that life's raw materials are widespread in the universe, increasing the likelihood of its emergence. Extremophiles challenge the notion that life requires Earth-like conditions. Organisms like the tardigrade can survive in the vacuum of space, extreme radiation, and intense heat. These resilient creatures suggest that life might emerge in environments we once deemed uninhabitable. Moreover, the search for exoplanets has revealed thousands of potentially habitable worlds. Some of these planets orbit stars similar to our Sun within their own Goldilocks zones. Could these planets host life? If so, it would support the idea that life is a universal phenomenon, not a unique accident. Yet, if life is inevitable, why have we not found definitive evidence of it beyond Earth? This paradox, known as the Fermi paradox, challenges the necessity hypothesis. Are we simply not looking in the right places, or is life's emergence rarer than we assume? The silence of the cosmos raises as many questions as it answers. Think of life as a seed planted in fertile soil. The conditions, sunlight, water, nutrients, make growth inevitable. Similarly, when the universe provides the right soil and climate, life, like a seed, is destined to flourish. The necessity hypothesis paints life as an intrinsic part of the universe, woven into its very fabric. This perspective shifts the narrative from randomness to inevitability, suggesting that wherever the universe creates the right conditions, life will arise. Design, a higher consciousness behind life. What if the emergence of life was not a product of random chance or inevitable natural laws, but a deliberate act of creation? The design hypothesis proposes that life's complexity and the universe's apparent fine-tuning point to the influence of a higher intelligence, a consciousness that set the stage for life to arise. Imagine a watch found on a beach. Its intricate gears and precision are unlikely to have formed by accident. Similarly, proponents of this view argue that life's complexity, from DNA's coded instructions to the universe's finely tuned physical constants, suggests a purposeful design rather than coincidence or inevitability. The idea of a higher consciousness shaping life is deeply rooted in philosophical and spiritual traditions. Religious perspectives, creation stories from various cultures such as Genesis in the Bible, Brahma's creation in Hinduism, or the Dreamtime of Aboriginal Australians, often portray life as the intentional work of a divine being or higher force. Philosophical inquiry. Ancient philosophers, including Plato and Aristotle, posited the existence of a prime mover or intelligent designer who set the cosmos into motion. These narratives resonate with the design hypothesis, reflecting humanity's long-standing intuition that life and the universe may hold deeper meaning and purpose. The fine-tuning of the universe. Certain physical constants, such as the strength of gravity, the charge of the electron, or the cosmological constant, are finely balanced. Even the slightest deviation in these values would render life impossible. For example, if the strength of gravity were slightly weaker or stronger, stars could not form or sustain nuclear fusion, eliminating the possibility of planets and life. The fine-tuning argument suggests that these precise values are unlikely to have arisen by chance, pointing instead to intentional calibration. The DNA code as evidence of design. DNA, often referred to as the blueprint of life, is a molecular code that governs the development and functioning of all living organisms. Its complexity and specificity have led some scientists and philosophers to liken it to a computer program. Could such intricate programming have arisen without an intelligent programmer? Irreducible complexity. Some biological systems, such as the bacterial flagellum or the human eye, are so complex that they seem irreducible, incapable of functioning if any single part were removed. Proponents argue that such systems challenge the gradualist explanations of evolution, suggesting a designer's hand. While compelling, the design hypothesis has faced significant criticism. Anthropocentrism. Critics argue that intelligent design is anthropocentric, projecting human notions of purpose and complexity onto the universe. Lack of empirical evidence. Unlike scientific theories that can be tested and falsified, intelligent design often relies on inference, which some dismiss as unscientific. Alternative explanations. Mechanisms like evolution and natural selection offer robust explanations for life's complexity, reducing the need for invoking a designer. In recent years, some scientists have explored ways to reconcile the idea of design with empirical evidence. Simulation theory. The hypothesis that our universe is a simulation designed by an advanced intelligence. Proponents like physicist Nick Bostrom argue that if future civilizations develop the technology to simulate universes, it's statistically likely that we are living in one. Panpsychism, a philosophical view suggesting that consciousness is a fundamental property of the universe, embedded in all matter. In this framework, the universe's design could emerge from a collective consciousness rather than an external creator. To understand the design hypothesis, think of life as a symphony. The universe is the orchestra, and its laws are the instruments. A symphony requires a conductor to arrange the notes into harmony, just as life's emergence might require a designer to orchestrate the right conditions. Comparative analysis overlapping themes and conflicts. Despite their differences, the three perspectives, coincidence, necessity, and design, share common ground in addressing the profound mystery of life's origins, the uniqueness of life. All three views recognize that life is extraordinary, whether it emerged by accident, inevitability, or design. Each perspective underscores the rare and complex nature of living systems in a vast, seemingly indifferent universe. Interplay between chaos and order. the coincidence hypothesis highlights the chaotic randomness of molecular interactions. The necessity hypothesis demonstrates how order emerges naturally from the laws of physics and chemistry. The design hypothesis emphasizes intentional order, suggesting chaos is merely the backdrop for a purposeful plan. The role of universal laws. All three approaches acknowledge the importance of the universe's physical and chemical laws. Whether these laws create life by chance, inevitability, or design, they are fundamental to the discussion. While the shared themes bring the perspectives together, their underlying assumptions often lead to sharp contrasts. Chance versus determinism. Coincidence relies on randomness, viewing life as the result of improbable events. Necessity emphasizes determinism, positing that life is a predictable outcome of universal principles. Design versus naturalism. The design hypothesis introduces the idea of a higher intelligence or purpose, while coincidence and necessity remain rooted in natural processes, rejecting the need for external intervention. Philosophical implications. Coincidence suggests life has no intrinsic meaning, as it is a random occurrence. Necessity offers a middle ground, implying that life has significance as a natural product of the universe. Design infuses life with purpose, proposing that it is part of a deliberate cosmic plan. Some thinkers argue that these perspectives are not mutually exclusive but could instead represent different layers of the same reality. The coexistence of chance and necessity. Life's origins could involve a combination of random events and deterministic laws. The formation of essential molecules might be random, but their assembly into complex systems could follow inevitable patterns. Design through natural processes. The design hypothesis doesn't necessarily conflict with science. A higher intelligence might have created the universe's laws in such a way that life emerges naturally, with occasional elements of randomness shaping its path. To visualize these perspectives together, imagine a painter creating a masterpiece. Coincidence. The paint splatters randomly on the canvas, forming an unplanned image. Necessity. The painter uses precise strokes guided by the properties of the brush and paint, ensuring the painting emerges logically from the tools. Design. The painter has a vision from the start, intentionally guiding every element of the painting toward a final purpose. Perhaps life's origins resemble a collaboration between these approaches, an interplay of chaos, inevitability, and vision. The origins of life remain one of humanity's greatest mysteries, inspiring theories that range from randomness to inevitability to intentional design. Coincidence reminds us of life's fragility, portraying it as a miraculous anomaly in a chaotic universe. Necessity elevates life to a fundamental feature of the cosmos, a product of its inherent laws and principles. Design introduces purpose, suggesting that life may be the deliberate creation of a higher intelligence. Each perspective provides a compelling lens, yet none alone can fully explain the profound complexity and meaning of life's emergence. As we journey through these ideas, one question emerges: must we choose just one? Perhaps life's origins encompass all three perspectives in a complex interplay. Coincidence could describe the unpredictable initial conditions that led to life. Necessity could explain the universal laws that guided its development. Design might reflect an underlying purpose woven into the fabric of the cosmos. Much like a mosaic, the full picture of life's origins might only emerge when we consider these perspectives together, embracing their unique insights and shared mysteries. The exploration of life's origins ultimately leaves us with more questions than answers. If life is a cosmic accident, how do we make sense of its meaning, or lack thereof? If life is inevitable, what responsibilities do we have as part of the universe's natural progression? If life is designed, what role might humanity play in a grander plan? As we contemplate these questions, we are reminded that the journey to understand life's origins is as important as the answers themselves. As we gaze into the night sky, marveling at its vastness and mystery, one truth becomes clear: our existence is an extraordinary phenomenon, whether born of chance, necessity, or design. It is up to us to make meaning from this knowledge, to explore with curiosity, and to live with purpose. For in the grand tapestry of the universe, we are both its observers and participants, a fleeting but vital spark in the eternal story of existence. Everything we know represents just 5% of the universe. What is the rest? Normal matter protons, neutrons, and electrons make up just 5% of the universe. Staggeringly, the other 95% is something which we cannot fathom, see or understand. We call it dark matter, which makes up 27% of the universe, and dark energy, which makes up 68%. But what are these mysterious components of our universe? Dark matter and dark energy are two mysterious concepts in astrophysics that scientists use to explain some of the strange observations that we make about the universe. Dark matter is a type of matter that does not interact with light or any other form of electromagnetic radiation. This means that we cannot directly detect it using telescopes or other instruments that rely on light. However, scientists can infer its existence by observing its gravitational effects on visible matter, such as stars and galaxies. Dark matter is thought to make up about 85% of the total matter in the universe, but we still do not know what it is made of. It does not behave like any of the known particles that make up ordinary matter, such as protons and electrons. Some theories propose that dark matter consists of undiscovered particles that do not interact with light or other forms of radiation, while others suggest that it may be made up of exotic objects such as black holes. Dark energy, on the other hand, is a hypothetical form of energy that is thought to permeate all of space and is responsible for the accelerating expansion of the universe. Unlike dark matter, which has a gravitational effect that slows down the expansion of the universe, dark energy has a repulsive effect that causes the expansion to speed up. The exact nature of dark energy is not well understood, but it is thought to be a property of space itself, rather than a type of matter or energy that we can directly observe. Scientists believe that dark energy makes up about 68% of the total energy in the universe. How many dimensions does the universe have? To the best of our knowledge, the universe as we know it has three spatial dimensions: length, width, and height, and one dimension of time, making a total of 4 dimensions in spacetime. This is known as the four-dimensional spacetime. However, some theories in physics, such as string theory, propose that there may be more than 4 dimensions, possibly up to 11 dimensions. But these extra dimensions are thought to be curled up or compactified to be too small to be observed at our scale. This means that although they may exist, they are not directly observable, and their effects on the four-dimensional spacetime can only be inferred through their influence on the physical phenomena that we can observe. These additional dimensions would help us unify the mathematical basis of the 4 fundamental forces of nature: the strong nuclear force, the weak nuclear force, the electromagnetic force, and gravity. Do these higher dimensions exist? And if they do, is there a way for us to measure their presence? Or will we forever be trapped in our 4-dimensional world? What if our universe is just one of a multitude out there? The idea that our universe is just one of many universes, known as the multiverse theory, is a popular concept in modern cosmology and physics. According to this theory, there may be many other universes existing alongside our own, each with its own unique properties and laws of physics. If this is the case, it would have profound implications for our understanding of the universe and our place in it. For example, it could help explain why our universe appears to be finely tuned to support life, known as the anthropic principle. If there are countless other universes with different physical laws and properties, it would increase the chances of at least one of them being able to support life. The multiverse theory also raises questions about the nature of reality and how we define what is real. If there are many different universes with different physical laws, are they all equally real? Or is our universe the only real one? What is time? Time is one of the most difficult properties of our universe to understand. Researchers say that time is a measurable period, a continuum that lacks spatial dimensions. There seems to be an obvious direction of time, and it seems we can't travel backwards in time. Why is this? Are we trapped in the arrow of time, perpetually moving forwards? Is the passing of time intertwined with the way our universe works? According to the theory of Big Bang, time itself began together with the rest of the universe about 13.8 billion years ago. Does that mean that it makes no sense to ask what was there before? Time is a fundamental concept in physics and is often defined as the progression of events from the past, through the present, and into the future. It is a fundamental dimension in which events occur and is often represented as a continuous line or axis. In the context of physics, time is typically measured in units such as seconds, minutes, hours, and years. It is also an essential component of the space-time continuum, which is the four-dimensional fabric of the universe, consisting of 3 spatial dimensions and 1 temporal dimension. The flow of time is often described as being unidirectional, meaning that it moves forward and cannot be reversed. This is known as the arrow of time and is often associated with the second law of thermodynamics, which states that entropy, the measure of disorder or randomness, in a closed system tends to increase over time. The nature of time is still a topic of ongoing research and debate in physics and philosophy. Some theories propose that time is an emergent property that arises from the complex interactions of the universe's fundamental components, while others suggest that time is a fundamental property of the universe, akin to space and matter. Particles violating the laws of nature. In certain situations, 2 particles can seemingly be in instant connection with each other, even if they are located at opposite ends of the universe. The phenomenon is known as quantum entanglement, where 2 particles can become correlated in such a way that the state of one particle is instantly correlated with the state of the other, regardless of the distance between them. While this may seem like a violation of the laws of nature, it is actually consistent with the principles of quantum mechanics. However, it is important to note that this does not allow for faster-than-light communication or the violation of causality. This is because while the state of the entangled particles may be instantaneously correlated, there is no way to control or manipulate this correlation to transmit information faster than the speed of light. In fact, there is a fundamental principle in quantum mechanics known as the no-communication theorem, which states that it is impossible to use entanglement to transmit information faster than the speed of light. So while quantum entanglement may seem like a strange and mysterious phenomenon, it does not allow for the violation of the laws of nature or the principles of causality. Could this feature of quantum mechanics one day allow us to send information instantaneously over large distances? Are we alone in the universe? There are at least 2 trillion galaxies in the observable universe with more stars and planets in them than all the grains of sand on planet Earth. So, where is everyone? Why haven't we encountered life from elsewhere? Is life incredibly rare? Or does it have a limited lifetime, destroying itself before it has had the chance to seek out other life forms? What does this tell us about the future of humankind? The question of whether or not we are alone in the universe is one of the most intriguing and profound questions we can ask. Given the vast size and age of the universe, it seems unlikely that Earth is the only planet with the conditions necessary for life to emerge. There are likely billions of potentially habitable planets in our galaxy alone. However, the fact that we have not yet encountered any definitive evidence of extraterrestrial life is known as the Fermi paradox. There are many potential explanations for the Fermi paradox, including the possibility that life is indeed rare, that it is difficult for life to evolve beyond a certain point, or that intelligent civilizations have a limited lifespan and self-destruct before they can explore the galaxy. It is also possible that we simply have not looked in the right places yet. Our current methods of searching for extraterrestrial life are still relatively limited, and it is possible that more advanced techniques in the future could uncover evidence of life elsewhere in the universe. Does the self-reference problem distort our perception of the universe? We humans are also part of the universe we inhabit, so when we look out to study the stars and galaxies, are we really neutral observers of the universe? When we explore the universe, we are both observers and the subject of observation. How can we pretend to be neutral when we are deeply embedded in what we explore? Could it be that this self-reference problem affects the way we look at the universe and gives us an overwhelmingly wrong impression? The self-reference problem is indeed a complex issue when it comes to our study and perception of the universe. We are not neutral observers of the universe, but rather we are embedded within it. This self-reference problem can lead to potential distortions in our perception of the universe, as we may unwittingly project our own preconceptions and assumptions onto our observations. For example, we may tend to focus on phenomena that we find particularly interesting or relevant to our own existence, rather than taking a more objective and comprehensive approach. By acknowledging our own biases and limitations, we can work to develop more rigorous and objective methods of observation and analysis. Why is the universe seemingly so perfect for us? The universe seems to be perfectly made for us, but why is this? Why do the fundamental constants of our universe, such as the speed of light, have the values that they do, allowing life to exist? Could it be that there are infinite universes with infinite possibilities, and we merely happen to live in one that is perfect for life? There are a few possible explanations for this apparent fine-tuning of the universe. One possibility is the anthropic principle, which states that the universe is the way it is, because it must be compatible with the existence of observers. In other words, the universe appears fine-tuned for us, because if it were not, we would not be here to observe it. This is sometimes referred to as the selection effect. Why is it easier to destroy something than to put it back together? Entropy is the amount of disorder, chaos, or randomness in a system. One can never reduce entropy. Everything in the universe slowly moves towards disorder. It's very easy to smash a window, but impossible to put it back together exactly as it was before. The principle of entropy moves the universe from structure to chaos, from an ordered state to disorder. What does this tell us about the fate of the universe? As the universe continues to expand, it will eventually reach a state of maximum entropy, where all matter is uniformly distributed and there is no energy gradient available to drive further processes. This state is known as the heat death of the universe, where the universe will be cold, dark, and lifeless. The universe is not a closed system, as it receives energy from stars and other sources, but the overall trend is towards increasing disorder and chaos. However, it is important to note that this process will occur over an extremely long time scale, likely trillions of years in the future. Can anything escape a black hole? We have observed the effects of black holes, and we have seen one directly. The gravitational force of these massive objects pulls everything towards them, even light itself. What happens in the mysterious, infinitely dense center of a black hole? Could there exist such things as white holes, the opposites of black holes, that spew matter and time into our universe? According to our current understanding of physics, nothing can escape a black hole once it has passed the event horizon, which is the point of no return. The gravitational pull of a black hole is so strong that it warps space and time, and anything that crosses the event horizon is inevitably pulled towards the singularity at the center of the black hole, where the laws of physics as we know them break down. We do not know what happens at the center of a black hole, as our current understanding of physics is unable to describe the conditions there. It is commonly believed that the matter at the singularity is infinitely dense and compressed to a point of zero volume, known as a singularity. As for the possibility of white holes, which are hypothetical objects that are the opposite of black holes, there is currently no direct evidence to suggest that they exist. White holes are hypothetical objects that are believed to exist at the other end of a hypothetical wormhole, which is a hypothetical tunnel-like connection between 2 points in spacetime. However, there is no direct evidence to suggest that wormholes exist either. From Einstein's theory of relativity to the mind-bending mysteries of quantum mechanics, from the explosive origins of the Big Bang to the eerie invisibility of dark matter, these ideas are not just theories. They're gateways to a universe beyond imagination. But what if there's more? What if our universe is just one of many? Or brace yourself, what if we're all living in a simulation? Embark with us on a journey to uncover the universe's greatest mysteries, diving into mind-bending theories that will expand your imagination. Together, we'll travel through the cosmos, unlocking the secrets of existence. Theory of relativity. Developed by Albert Einstein in the early 20th century, This theory reshaped our understanding of space, time, and gravity. It's divided into two parts: general relativity and special relativity, each revealing unique insights about the universe that continue to shape science today. Let's dive into general relativity, introduced by Einstein in 1915. Unlike earlier concepts of gravity as a force acting across space, general relativity describes gravity as a result of curvature in the fabric of space-time. Picture a stretched-out trampoline with a heavy ball in the center. The weight of the ball creates a dip, causing smaller objects to move toward it. In the same way, massive objects like stars and planets create similar dips in space-time, which draws other objects toward them. This is how general relativity redefines gravity as the bending of space and time itself. This idea of space-time as a four-dimensional entity where mass and energy can cause a curvature was groundbreaking. The closer an object is to a massive body, such as a planet or a star, the stronger the gravitational effect it feels due to this curvature. In 1919, general relativity received its first experimental confirmation during a solar eclipse. Astronomers observed that starlight passing close to the sun was bent, just as Einstein had predicted. This phenomenon, known as gravitational lensing, occurs because massive objects, like the sun, bend the space around them, causing light to follow a curved path. Today, gravitational lensing remains a valuable tool in astronomy, allowing scientists to study distant galaxies and even detect objects that would otherwise be invisible. The implications of space-time curvature are profound. For example, in areas where mass is exceptionally dense, such as in black holes, space-time curvature becomes so intense that it collapses into what's known as a singularity, where gravitational forces become infinitely strong. At a singularity, the known laws of physics break down, creating an area where even time may cease to exist as we understand it. Einstein's equations in general relativity also hinted that the universe could not be static, eventually leading scientists to discover the expansion of the universe and support for the Big Bang theory. This concept is foundational in cosmology and helps us understand the vast structure of the universe. Moving to special relativity, which Einstein introduced in 1905, we encounter another revolutionary idea: the speed of light is constant, regardless of the motion of the observer or the light source. Special relativity specifically applies to objects moving at constant, non-accelerating speeds and fundamentally changes how we understand time and space. According to this theory, as an object nears the speed of light, time slows down for it relative to an outside observer. This phenomenon, called time dilation, has been observed in experiments where fast-moving particles and clocks flown around Earth experience measurable time differences. For example, GPS satellites in orbit need corrections for time dilation to maintain accurate navigation on Earth. Two critical concepts arise from special relativity: time dilation and length contraction. Time dilation means that time slows down for objects moving at high speeds. This could theoretically allow for long-distance space travel, where astronauts could experience only a few months while years pass on Earth. Length contraction, on the other hand, states that objects in motion appear shorter in the direction they are moving. This effect is only noticeable at speeds close to the speed of light, making interstellar distances appear shorter for high-speed travelers. Together, these concepts reshape our understanding of time, space, and even the feasibility of human space exploration. One of the most famous outcomes of special relativity is the equation E equals mc squared, which reveals that energy is equal to mass times the speed of light squared. This equation implies that mass and energy are interchangeable, meaning that even a small amount of mass can release a tremendous amount of energy. This principle forms the foundation of nuclear energy and explains why stars emit so much light and heat through nuclear fusion. In nuclear reactions, tiny amounts of matter are transformed into vast quantities of energy. This equation also led to predictions about antimatter and other exotic forms of matter, enriching our understanding of particle physics and cosmology. Despite its success, relativity isn't without challenges. General relativity, which describes large-scale phenomena like stars and galaxies, doesn't align well with quantum mechanics, which governs atomic and subatomic particles. The pursuit of a unified theory that combines both realms, often called the theory of everything, is one of the biggest goals in theoretical physics, with approaches like quantum gravity and string theory attempting to bridge this gap. Furthermore, general relativity's predictions about black holes and singularities hint that our understanding of space-time might still be incomplete. Observations of phenomena like dark energy, which accelerates the universe's expansion, suggest there are aspects of physics yet to be discovered. Though it may seem abstract, relativity has practical applications in everyday life. For instance, the Global Positioning System, GPS, relies on relativity-based adjustments, as satellites orbiting Earth experience different gravitational and speed effects on time. Without these adjustments, GPS accuracy would quickly degrade. Relativity also plays a crucial role in particle accelerators, which must account for relativistic effects as particles approach light speed. The Large Hadron Collider, for example, uses these principles to ensure the accuracy of high-energy particle physics experiments. In summary, the theory of relativity transformed how we perceive the universe by demonstrating that space and time are interconnected and can be influenced by gravity and motion. General relativity redefined gravity through space-time curvature, while special relativity reshaped our understanding of time, speed, and energy. Together, these theories form the backbone of modern physics and continue to inspire new technological and scientific advancements. But relativity is only the beginning. As we venture further into the mysteries of black holes, time travel, and the expanding universe, we may yet uncover even more mind-bending truths about reality. Now, let's explore the next mind-bending concept: quantum mechanics. This theory explains the behavior of particles at microscopic scales, where classical physics no longer applies. Quantum mechanics introduces us to a world governed by probabilities, uncertainties, and phenomena that challenge our understanding of reality. One of the cornerstones of quantum mechanics is wave-particle duality, which suggests that particles like electrons and photons can behave both as particles and as waves. In the classic double-slit experiment, particles fired at a barrier with two slits create an interference pattern, behaving like waves. However, if we observe which slit each particle passes through, they act like particles again, as though the act of measurement changes their behavior. This mysterious link between observation and reality questions the very nature of existence. Next, we have the uncertainty principle, proposed by Werner Heisenberg in 1927. It states that we can't know both the exact position and momentum of a particle at the same time. The more precisely we know one, the less precisely we can know the other. This isn't due to measurement limitations, but is a fundamental property of quantum particles, adding an element of randomness and unpredictability to the quantum world. Imagine you have a ball moving along a path. In classical physics, you can measure both its speed and position accurately. However, in quantum mechanics, if you try to measure an electron's exact position, you inherently alter its momentum, making precise measurement impossible. Quantum superposition takes uncertainty a step further. It states that particles can exist in multiple states simultaneously until observed. Erwin Schrödinger famously illustrated this with a thought experiment: Schrödinger's cat. Imagine a cat in a sealed box with a vial of poison. If a radioactive atom decays, the vial breaks, killing the cat. Until we open the box, the cat is in a superposition of being both alive and dead. This paradox highlights how observation affects outcomes in the quantum world. Superposition has practical applications, especially in quantum computing. Quantum computers utilize qubits, which can exist in multiple states at once, allowing them to perform vast amounts of calculations simultaneously. This gives quantum computers the potential to solve complex problems far beyond the reach of classical computers. Quantum entanglement is one of quantum mechanics' strangest phenomena. When particles become entangled, the state of one instantaneously affects the state of the other, no matter the distance. If we measure one particle, we instantly know the state of the other, even if they're light years apart. This phenomenon, called spooky action at a distance by Einstein, challenges the idea that objects are only influenced by their immediate surroundings. Entanglement has significant implications for quantum communication and cryptography. The Copenhagen interpretation, developed by Niels Bohr and Werner Heisenberg, suggests that quantum systems exist in superposition until observed, causing them to collapse into one definite state. This raises profound questions. Does reality depend on consciousness? If observing a particle can change its state, what role does our mind play in shaping the physical world? This interpretation bridges physics with philosophical debates about the nature of reality. In contrast to the Copenhagen interpretation, the many worlds interpretation proposes that all possible outcomes of a quantum event actually occur, each in a separate universe. For example, in Schrödinger's cat experiment, one universe would have a live cat and another would have a dead one. The many worlds interpretation implies a multiverse of branching realities, each representing different outcomes, avoiding the need for wave function collapse. While it sounds like science fiction, this interpretation has gained popularity among physicists. Quantum mechanics has led to groundbreaking advancements in technology, especially in computing, cryptography, and telecommunications. Quantum computers, for example, use qubits that can represent both 0 and 1 simultaneously, enabling them to solve complex problems much faster than classical computers. Quantum cryptography uses entanglement to develop unbreakable encryption methods. Quantum teleportation, although not teleportation in the science fiction sense, uses entanglement to instantly transfer information, potentially revolutionizing secure communications. Quantum mechanics presents philosophical and scientific challenges that stretch beyond physics. Unlike the deterministic world of classical physics, the quantum world introduces probabilities, where outcomes depend on observation, challenging ideas of objective reality. Quantum mechanics has inspired numerous interpretations and debates. Is reality independent of observation, or does our consciousness shape it? These questions bridge the realms of science and philosophy, making quantum mechanics one of the most existentially provocative theories. To summarize, quantum mechanics defies conventional understanding with concepts like wave-particle duality, uncertainty, superposition, and entanglement. This theory challenges classical physics, introducing a probabilistic and interconnected universe that pushes the boundaries of what we know. Quantum mechanics has paved the way for technological breakthroughs in computing and cryptography, yet leaves us questioning the nature of reality itself. As we journey deeper into these mysteries, quantum mechanics will continue to shape our understanding of the universe and invite us to rethink reality. Let's move on to string theory, an ambitious and mathematically complex theory that aims to unify all of the fundamental forces in nature and provide a theory of everything. String theory suggests that the fundamental building blocks of the universe aren't particles like electrons or quarks, but incredibly tiny, vibrating strings. These strings and their vibrations supposedly give rise to all particles and forces, making string theory one of the most promising yet confusing approaches in modern physics. At its core, string theory proposes that the building blocks of our universe are one-dimensional strings. Each string vibrates at a specific frequency, producing different particles and forces, similar to musical notes on a string instrument. For example, an electron and a photon would both be different vibrational patterns of a fundamental string, much like different notes produced by the same string on a musical instrument. One of the revolutionary aspects of string theory is its potential to unify quantum mechanics, the physics of the very small, and general relativity, the physics of the very large. While quantum mechanics explains the behavior of particles and relativity explains gravity, these two frameworks are currently incompatible. String theory could provide a way to reconcile them by offering a single, coherent framework that accounts for all known forces and particles. Multiple versions of string theory emerged in the 1980s, leading to confusion. However, physicist Edward Witten introduced M-theory, uniting these versions into one overarching framework. M-theory suggests that strings may not be the only fundamental structures. Higher dimensional objects called branes, short for membranes, might also exist. These branes could be as small as a single point or as vast as a universe, adding a whole new layer of complexity to the theory. According to M-theory, our own universe might be a three-dimensional brane floating within a higher dimensional space, possibly interacting with other branes and universes. One of the most challenging and mind-bending aspects of string theory is its requirement for additional spatial dimensions. In everyday life, we experience 3 dimensions of space and 1 dimension of time. However, for string theory's equations to work, 10 or even 11 dimensions are required. The additional dimensions in string theory are hypothesized to be compactified or curled up so small that we can't perceive them. Imagine a 2-dimensional sheet of paper curled into a tight spiral. If you zoomed out far enough, it would appear as a 1-dimensional line. In a similar way, the extra dimensions in string theory could be curled up to scales smaller than an atom, making them invisible to us. The idea of extra dimensions, while mathematically sound, is almost impossible to visualize, adding to the confusion and intrigue surrounding string theory. These dimensions could hold the key to understanding forces that seem weak or mysterious in our familiar dimensions, such as gravity. Because string theory allows for many possible solutions, there may be an enormous number of vacua or possible configurations of the universe. Each configuration would correspond to a different set of physical laws and constants, leading to the possibility of a multiverse, an immense collection of universes, each with its own distinct properties. In other words, our universe could be one among countless others, each governed by different rules. This idea is both intriguing and problematic. If the multiverse is real, it would be impossible to test or observe directly, meaning we may never confirm or falsify its existence. Critics argue that this makes string theory difficult to treat as a true scientific theory, as it may lead to predictions that cannot be tested or observed. Despite its promise, string theory faces challenges. It lacks testable predictions, is mathematically complex, and some question if it qualifies as a scientific theory due to its non-falsifiable nature. Even without concrete proof, string theory has profoundly impacted physics and mathematics. Concepts from string theory have influenced quantum field theory and pure mathematics, leading to insights that extend beyond its original scope. Physicists continue refining string theory, hoping that future experiments or new technology will reveal supporting evidence. String theory offers a path to unify all fundamental forces, potentially revealing a theory of everything. Whether it leads to a revolutionary understanding or paves the way for future theories, string theory marks a bold step in our quest to unravel the cosmos mysteries. Approximately 13.8 million years ago, an enigmatic occurrence propelled the universe into motion, marking the advent of the Big Bang, an extraordinary event that gave rise to every atom, star, and galaxy. However, what unfolds here is uniquely ours, a saga spanning millennia where we've endeavored to construct a vision of the universe. This endeavor, guided by the principles of science, has allowed us to fathom our place within the vast cosmos. Over thousands of years, we've documented our celestial observations in volumes that could easily populate a library. The edifice of knowledge we've erected regarding our universe encompasses its origins and contemplates its eventual conclusion. So where does our narrative commence? Let's embark on this journey from the very outset. Let's delve into the genesis, starting with the monumental event known as the Big Bang. The concept of the Big Bang serves as a framework for understanding the cosmic evolution and unfolding narrative that illuminates how the universe transformed in the blink of an eye. The very nature of what sparked this cosmic genesis remains an unsolved puzzle to this day. As we peer into the vastness of the universe and contemplate distant galaxies, a mesmerizing panorama unfolds. Everything appears to be receding from us, propelled outward at astonishing speeds. We string that all the way back, we glimpse a singular moment, perhaps 13 or 14 billion years in the past, where all matter was inexplicably condensed into an inconceivably dense point. The Big Bang stands as our prevailing theory, a testament to our attempts to decipher the universe's inception. For an extended period, contemplation of the universe's origin was not a common pursuit. Some didn't dwell on it, while others assumed the cosmos had perpetually existed, an everlasting entity shrouded in mystery. Initially, even scientists hesitated to embrace the concept of the Big Bang. Originally intended as a somewhat derisive term, the name itself poses a paradox. It wasn't particularly big, considering our belief that the universe originated from a singularity, and there was no literal bang since there was no air to transmit vibrations. Today, the Big Bang theory is a well-established pillar of science, widely accepted and understood. However, acceptance and comprehension are distinct realms. While the Big Bang theory has solidified its place in our understanding of the universe, it hasn't yet unraveled all the mysteries science seeks to answer about the birth of our cosmos. Conventional Big Bang theory remains silent on what triggered the bang, why it occurred, or what transpired before it. At this very moment, we find ourselves in the aftermath of the Big Bang. Everything what we see and hear and taste and smell and touch is aftermath. This is the Earth, a marvel of silicon and oxygen encasing a metallic core. Its surface is dominated by vast oceans, fostering a diverse array of life. In a rhythmic dance, the Earth completes a full rotation every 24 hours while encircling the radiant star known as the Sun, completing an orbit every 365 days. The Sun, a radiant giant predominantly composed of hydrogen and helium. With a scorching surface temperature nearing 10,000 degrees Fahrenheit, this cosmic powerhouse converts a staggering 700 million tons of hydrogen into 695 million tons of helium every second. This celestial luminary is at the heart of our solar system, which took shape approximately 4.5 billion years ago. This system has 8 planets, from the sweltering Mercury to the frigid Neptune. Our solar system is no static entity, hurtling through space at a staggering 134 miles per second. It is part of a vast congregation of stars and stellar systems. This congregation, known as the Milky Way galaxy, around 200 billion stars. Among these, an estimated 6 billion may harbor planetary systems akin to ours. Our solar system orbiting the center of the Milky Way on one of its outer arms is just one member of a grand ensemble. The Milky Way is merely one among the vast expanse of more than 125 billion galaxies, constituting the observable universe. Indeed, the universe is colossal, and its enormity continues to expand. If we rewind time, we can witness the universe shrinking from a cosmic scale to a galactic one, then to the dimensions of our solar system, and further still until everything is confined within the confines of a studio, a coffee cup, and ultimately an atom. The vastness of the universe unfolds before us, a cosmic narrative expanding across unimaginable scales. Physicists have pieced together an approximate timeline of significant events in the cosmos' existence using telescope data and models of particle physics. From its beginning to its inevitable demise, we examine key points in the evolution of our universe here. Cosmic inflation era. The next cosmic confab was to rapidly expand in size. The universe may have expanded exponentially after the Big Bang, tearing off previously colliding parts of space. This period, known as inflation, is still mostly theoretical, but it has gained favor among cosmologists as a possible explanation for the striking similarity between distant parts of space. Attempts to detect this expansion in light from the early cosmos were reported in 2014. Nevertheless, further investigation revealed that the true culprit was nothing more than interplanetary dust causing interference. Quark gluon plasma. The temperature of the early cosmos was between 7 trillion 10 trillion degrees Fahrenheit or 4 trillion and 6 trillion degrees Celsius, just a few milliseconds after the Big Bang. Quarks, elementary particles ordinarily contained within protons and neutrons, were free to move about at these temperatures. These quarks were combined with gluons, carriers of the basic force known as the strong force, in a primordial that pervaded the whole universe. In particle accelerators on Earth, scientists have replicated these circumstances. In both terrestrial atom smashers and the early cosmos, the challenging to achieve condition only lasted for a few fractions of a second. The early epoch, the subsequent period of time, beginning perhaps in the neighborhood of a few thousandths of a second following the Big Bang, was a period of intense activity. The universe chilled as it expanded, creating an environment conducive to the merger of quarks into protons and neutrons. The cosmic neutrino background, which has not yet been detected by scientists, was created 1 second after the Big Bang, when the density of the cosmos decreased sufficiently for neutrinos to sail across space without interacting with anything. The first atoms, protons and neutrons, fused together during the first 3 minutes of the universe's existence, creating the isotope of hydrogen known as deuterium, along with helium and a trace quantity of the next lightest element, lithium. Yet, this procedure ceased as the temperature dropped. As temperatures settled down 380,000 years after the Big Bang, hydrogen and helium had free electrons to form the first neutral atoms. The cosmic microwave background, a remnant of this epoch first identified in 1965, was created when photons that had previously collided with electrons were able to be elbed without being disrupted. The Dark Ages. There was a lengthy period of time when nothing in the cosmos emitted any light. The cosmic Dark Ages refer to this time frame of around 100 million years. Because practically all of what astronomers know about the cosmos can be gleaned by studying starlight, this era remains exceptionally challenging to study. It's hard to piece together what happened if there are no stars to guide us. The first stars were formed when hydrogen and helium began to compress into massive spheres, some 180 million years after the Big Bang, creating hellish temperatures at their centers. After the neutral hydrogen atoms in interstellar space were broken apart into protons and electrons by the intense photons generated by early stars and galaxies, the cosmos entered a period known as cosmic dawn or reionization. It's hard to put a time limit on reionization. As it happened so soon after the Big Bang, its signals have been masked by subsequent gas and dust. Thus, the most that scientists can determine is that it was finished by around 500 million years after the Great Bang. Large-scale structure. Almost a billion years after the Big Bang, supermassive black holes developed at the cores of merging early galaxies. Intense quasars, visible from 12 billion light-years away, switched on and began emitting their bright beams of light. The universe's middle years. Throughout the subsequent few billion years, the cosmos underwent more evolution. Denser regions in the early cosmos drew more material due to gravity. A gorgeous filamentary cosmic web is the result of them slowly expanding into galaxy clusters and lengthy strands of gas and dust. Birth of the solar system. A yellow star with rings around it formed from a cloud of gas around 4.6 billion years ago in one galaxy. These accreted rings eventually became the 8 planets of our solar system, as well as numerous comets, asteroids, dwarf planets, and moons. Either the third planet out from the Sun retained a lot of water via this process, or it received a deluge of ice and water from comets later on. Earth and humanity. Little, primitive bacteria appeared on that third, watery world between 3.8 and 3.5 billion years ago. These organisms arose and progressed into amazing marine monsters and enormous dinosaurs that fed on leaves. Some 200,000 years ago, upright beings emerged, capable of contemplating the vastness of space and learning about the universe's origins. The end or not? It isn't the final chapter, of course. The future of the cosmos is still a mystery to physicists. It is dependent on our ability to accurately quantify the characteristics of dark energy, the unknown factor thought to be accelerating the expansion of the universe. All the stars in all the galaxies will have burned out, and even black holes will evaporate into nothing if the universe continues to expand forever, leaving behind a lifeless cosmos saturated with inert energy if this scenario comes to pass. Alternatively, the Great Crunch, a reversal of the Big Bang in which gravity triumphs over dark energy's expansionary force, will occur. The Great Rip, in which the cosmos rips itself apart, is another possibility if dark energy accelerates everything apart to greater and greater distances.